Live now. Okay, welcome out there. We are live with our online lecture with today's guest, August Lerche from Pneuhaus. Very happy to have Pneuhaus invited to give a talk on pneumatic structures and design, computational design, fabrication. I got interested in the work of Pneuhaus through social media, apparently, kind of following them on Instagram for a while, and they're doing really interesting stuff on a topic that's been around in architecture for quite a while already. I think it has become even more interesting now with digital fabrication technologies, giving many more people the opportunity to directly work with pneumatic structures. And so did we start in one of our seminars to kind of look into pneumatic structures, a seminar that is usually more kind of interested in space frame structures, 3D printing, and these things of kind of digital fabrication. And yeah, in that respect, I'm super happy to have August here today. Let me introduce August Lerche, who is by training a furniture designer. In 2014, 2 years after graduating, he founded Pneuhaus with two other founders. He will explain exactly what the business is, what the design is, what type of projects they're doing. August later on, just 2 years ago, went for a graduate degree at ITEC in Stuttgart, which he kind of graduated from last autumn. So he has a degree with architects, engineers, and other designers at ITEC. And I'm very curious to find out more about the work, how it blends computational design, fabrication, and actual making stuff, which I'm super interested in. August, it's over to you. People on YouTube, they're welcome to post questions in the chat, and we will discuss work afterwards from the questions in the chat and questions I have. So, stage is yours, very welcome. Thank you.
Great, thank you so much, Mirko, for the introduction. I guess first and foremost, because I'm giving a lecture in Germany, when we founded, we call it Pneuhaus when we founded it, but I would like to apologize to the Germans out there because we had no knowledge of pronunciation when we started. For us, new in the US stands for pneumatic. So, I mean, I'm sure it's very similar, but only later did we find out that it's a tire store, I think, in Germany. So that was kind of a fun discovery for us. But anyway, sorry for that. But thank you for the introduction. So today, as Mirko said, I'll be talking about our practice at Pneuhaus and sort of the various ways that we work with air. So first and foremost, Pneuhaus is not just me. We're 4 other people at the moment: Matthew Muller, and Levi Badal, who I co-founded Pneuhaus with in 2014. Matt has a background in furniture, and Levi actually has a background in architecture. And we were joined later by Stavely Kuzmanov, who's studied textiles, and Emily Shinada, who studied sculpture. And my background, Mirko already outlined. But in general, it's sort of grown over the years because we're not necessarily making architecture, we're making objects as well, and we'd like to keep it quite open conversation, so it's an interdisciplinary team. And in general, we are a studio that focuses around the craft of inflatables, we like to call it, because when we were looking at the numerous examples of pneumatics in architecture, we found there's usually sort of architects using these things that design them, but then somebody else fabricates them, and then another person entirely installs them. And so starting out, I mean, with the resources we had, it was sort of important to us that we integrate the design, fabrication, and installation all under one roof, mostly in the beginning because of resources, but as we developed and made more projects, it became sort of integral to how we think about the detailing, and sort of what makes something easier to install is usually something that you can include in the fabrication stage. So this integration is something that was really important to our craft. And in general, pardon my simple sketches for the engineers in the room, but pneumatics or inflatables are structures where flexible membranes are given tension through the differential pressure of a gas. So in most cases it's air, but it can be other things. And I always like introducing it in contrast to sort of a typical tent structure where compressive forces are usually passed through sort of rigid struts. With inflatables, the air sort of becomes the compressive element. So that's sort of an important thing to understand with inflatables. And I also like to start with an extremely concise sort of history of inflatables because, like Mirko said, it has a really rich history and has actually been used more and more today. But it's interesting to see sort of what time periods saw the most uses of inflatables in architecture. So precursing all of this, the biological world is sort of the first users of pneumatics, anywhere from sort of cell walls with differential pressure gaining structure to frogs' throats modulating acoustical properties. It's something that I think most of the natural world is soft, and you see that a lot today with explorations in soft robotics and things like that, but always good to nod to biology before any of this. But the first human-made uses of pneumatics is probably the sail, which varies who discovered it, but around 6,000 to 4,000 BC. And it wasn't until much, much later, sort of 1780s, when the hot air balloon was invented by the Montgolfier brothers as sort of just a human-made envelope that's meant to hold air. And it wasn't until sort of 1948, 1950s, when the first, I mean, some were theorized before this, but the first sort of built pneumatic structures were made for semi-permanent use. On the top left, you can see Walter Bird's gray domes, which he made these giant rubber domes over radars to protect them from weather and being seen. And going chronologically, on the bottom, you see Fry Otto, who I'm sure most of you are familiar with, who held the first symposium on pneumatic structures in Stuttgart in 1967, followed really closely by the 1970 Osaka World's Fair, where I think 3 or 4 of the country's exhibits that year were all pneumatic related, and I'm only showing one of them there. But I also like to show the last 3 as sort of examples of how in the 60s and 70s the plastics and sort of films were being very readily available to people, and you have artists like Ant Farm or Graham Stevens on the top right making these really large air cushions that they're just sort of experimenting with. The Ant Farm one is sort of part of this hippie movement where they theorized it could be this new nomadic type of architecture. And then in 1972, Koop and Blau's Oasis number 7 was another really cool example, I thought, where he sort of erected these space frames that shot out of buildings that had these pneumatic envelopes. And then there's another break here to more contemporary examples, because in 1973, there was an oil crisis, and a lot of these readily accessible plastic films kind of became much harder to find and use, or more expensive. And it wasn't until sort of like early 90s, 2000s that like architects and designers started using them again. I'm not sure, can you guys see the zoom? I'm gonna move my face. So the more contemporary examples I've chosen are sort of Tomas Saraceno's In Orbit, which is in Dusseldorf, I believe, where he sort of suspended these giant reflective spheres in these wire meshes, sort of a nod to new material properties, like you can get mirror film now, and very translucent, yes, UV resistant materials. And in 2011, Anish Kapoor's Arc Nova was another big inflatable structure, which is the first sort of nomadic concert hall. And the last two I have are Ontario's Celebration Zone, which was made in 2015, forgetting the name of the architects, but I like this one as sort of a really recent example of a very well-made, I know who made it, it was Tectonics in the UK, but very well-made, sort of wind-resistant, structural, inflatable shape. And then finally, in 2016, we saw the first inflated space module be installed on the International Space Station, which sort of, I like to put both ends of like the sail being the first, and now we have a very highly engineered technical inflatable in outer space. But I like to go back to Friado because, because he was sort of big thinker early on sort of the applications of pneumatic structures. He sort of imagined these utopian, huge spanning, lightweight envelopes that would be sort of micro habitats for Arctic regions or large water collection systems for irrigation and farming. And unfortunately, he didn't realize any of his pneumatic projects. He's much more known for his tent structures. And a lesser known fact, I think, was his relationship with Peter Stohrmeier, which was a tent company that he partnered with in the very beginning to make his Montreal exposition tents. And he's quoted in saying the week that he spent with Peter Strohmeier's company in Switzerland, I think, in 1953 was one of the most productive weeks of his life. And I think it just points to this marriage of craft and design thinking that I think led to a lot of his more realized, really innovative projects. That it wasn't the fact that he just had these ideas and had all this engineering behind it, but that he had this good partnership with the people that could make it. So just rounding out the history section, that's sort of why brings us into where we situate ourselves. Newhouse, as we were starting, was very much about exploration and play, and sort of the more spatial exploration of the sort of movements in the 60s and 70s. But we're also very much interested in modern production techniques and making things well that can actually, stand up or support humans, that, would then lend itself back to the more experiential uses of pneumatics. So we kind of like to put ourselves in between the high tech and the playful. So I'm going to go through a series of projects. I've sort of grouped them based off of certain topics that will hopefully give you information on, types of inflatables and how you can think about making them. So we'll start out with sort of the topology of inflatables, sort of what shapes they want to become. And these aren't really in chronological order of when we made them, but that won't really matter. It won't become apparent later. And then we'll go into high pressure systems, so sort of using inflatables as sort of stiff members that can hold more weight. Then we'll go into sort of transparent qualities of inflatables, like using them for light and color transmission. Finally, going into the flexibility and adaptability of them. So the unique property of them is they can exist in different states. So projects that leverage, the collapsed state as much as the inflated state. And then I'll finally end by looking at sort of projects that we're interested in moving forward with, where we are now. Just a really quick section about what we're working on. So I always like to start with this project, just probably like the 4th or 5th inflatables we made in our career, but I think it kind of gets at really simple qualities of pneumatics. We made it when we were artists in residence at the Maryland College of Art, and they were sort of asking us to make a show based off of whatever we wanted, basically. But we used the time to reflect on just inflatables spatially in general, and we chose to make really simple explorations of this idea. And one of the main things that we found when we started making them, and this is pretty simple, is all inflatables want to become spheres, or at least circular in cross section. So you can imagine just sewing a cube together and it inflates to be this sort of pinched sphere-like shape, and the corners will probably bulge out weirdly because seams tend to stretch less than the fabric itself. And so when you're making inflatables, usually you have to like break down a shape to smaller and smaller pieces to closer approximate that doubly curved spherical shape. But the nice thing about inflatables is that you don't have to break them up into nearly as many pieces as you would if you were making it out of paper or something like that, because the internal pressure creates the double curvature when you inflate it. So that's something you kind of have working with you when you are working with pressure systems. So here's sort of an example of a spherical shape that we made for the show using using quads and triangles. During that time, we were also sort of thinking on, it's supposed to be a gift, but we were also thinking about sort of the space between spheres. Like we were thinking of spherical properties as sort of something inherent to inflatables, and we started exploring with tiling spheres in space. And we found that when you tile spheres, they kind of exist. The negative space creates sort of two repeating interlocking units, which we sort of would print out and play with. And the reason we got interested in this is because if the positive pressure system is the sphere, we wondered if we would be able to create sort of the inverse of it using a vacuum pressure. So on the left, I'm just gonna play a quick little video. We were messing around with sucking air out of membranes in the studio. And it's probably hard to see, but in order to create this, because it wasn't supported by air, or it's supported by the lack of air, we needed to make a frame for this vacuum chamber, which we did out of really simple bentwood strips. And, oh, sorry, did I lose full screen? I hope not. So we made these two spaces, both vacuum chamber and pressure chamber, and we sort of put them in this black box gallery so people could walk around each space, but also go inside of them. And for us, the spatial qualities also had this inverse, or the other properties had this inverse association, where the acoustics in the sphere were really intense, because if you said anything, all of the sound would rebound to a single point, whereas in the other space, all the sound was sort of dispersed and muffled towards the edges. So we kind of used this show as an opportunity to explore just kind of the binary you get with membranes, because you're working with just a single layer of fabric, and the templating for these two are exactly the same, but it's just sort of the relationship you share with the surface around you. So just to round out this project, this is what a typical model for this type of project looked like. This was really early on. We were cutting everything out by hand. So we tended to make really symmetrical forms because that meant we needed to make a template for each unique piece of fabric that were to be cut. So all the different colors you see there are unique types of pieces, and what we ended up doing was just stacking a bunch of fabric, cutting out the piece, and organizing it how you see in the middle there. But we usually sort of have a working Rhino file when we're working through this stuff, just to show you the in process. And then when we go to install it, it's another thing entirely, because we wanted people entering each space to sort of, like for the vacuum chamber, be supported by the vacuum, but we found quickly that the pressure we had wasn't nearly enough. And we had to sort of come up with this solution where we put a positive pressure cushion underneath the vacuum space, so people going into the space would be able to be supported sort of by air. And it's just, I put this slide in just to show how, you know, the idea of a thing, and, you know, when it comes to installing it, you have to make these last minute decisions or sort of realizations if you want it to be used the way you imagined it. So installing becomes this key factor. And so the next project, sorry, I'm gonna, I don't want to mess with that. Okay, so the next project, once you start moving away from the topology of a simple sphere or something like that, you kind of it gets very hard to know how to rationalize inflatables, because they want to act in very different ways depending on the input conditions. So this next project, which we called handles, we kind of explored more complex topologies away from spherical symmetrical shapes. And it really started with just making physical plaster models that we had been making in the studio for a while, where we filled a latex balloon with plaster and then would sort of clamp these earth magnets onto them. And when the plaster dried and it was removed, you get these really nice rounded out voids in the balloon shape. And it was really nice because you could put the magnets in different locations, and the latex would be flexible enough to sort of expand and sort of naturally assume these pneumatic shapes. And we really wanted to make larger versions of these. To do this, you could use latex on a larger scale, but it's notoriously hard to join, and it wouldn't be nearly as strong as if we made it out of a fabric. So we needed to figure out a way to model this material distortion and be able to then cut it out of already made fabrics. So we to scale this sort of material properties of the latex, we made some very simple modeling tools in Rhino and Grasshopper, where we would have like an input curve, and we would mesh the input curves and inflate it in with using Kangaroo. And in the beginning, we would just start discretizing that mesh into linear strips, which we then smoothed and turned into unrollable, developable curves that we would then label and assemble. This was still before our, we were still cutting everything out by hand. So we would end up we would end up making a piece of paper for each one of these unique pieces. But the tool was really nice because it let us get these cut files pretty instantaneously and begin iterating just through the formal possibilities of the process. And I think we've made 10 or 12 different shapes, both standing and hanging. We kind of treat them as these monolithic lights that put up for street festivals or music festivals. And I always like showing a picture of the inside of these, because we've always wanted to make a larger version that you could go inside of, but you also can sort of see where the material properties of the fabric begins to fail with the pneumatic shape. Like on the left here, you can see the wrinkles forming on the inside of the donut, where it doesn't want to stretch negatively in both directions. So we actually recently made some new ones, which I think are much smoother than our old work, where we actually keep the seam lines of the inflatable in the simulation itself. So instead of breaking it up after the pneumatic shape has been found with Kangaroo, it's integrated into the simulation process. And we found that creates a much smoother line for the end-all for the end-all pieces that would then later be unrolled. Just showing you some updated strategies on an old project. So the next project, just shifting gears a bit from topology to more structural aspects. And I say structure in quotes just because I'm referring to high pressure system, so more structural than, say, the continuous air, which the previous two projects were. And so in general, when you have membranes that are airtight and can be filled, they can be filled to much higher pressures because they can build up a lot more pressure in the membrane. And at the time we did this project, we didn't have any tools to weld any films together. And but we were really interested in sort of the qualities of airtight inflatables. So we ended up buying a lot of 3-foot beach balls and started playing around with just using pre-made beach balls as modules for this building system we were imagining, which we called Pneumatic Masonry. And the first idea we had was to try and use the same size building block and use sort of the flexibility of the pneumatic ball to be able to conform to different modules and shapes, and first and foremost try and create a dome with that logic. So this is sort of the first mock-up we made. You can see Matt, one of the founders, on the left with a string and ball model. But the basic idea was making these harnesses that we would then put the inflatable in, and the harnesses would have the geometry of both. We decided on making 3 different modules: triangles, pentagons, and hexagons, the blue, green, and red you see in this drawing. And so we'd sew harnesses into those 3 geometries and put the inflatables in and lash them together. And so this is sort of a video of the first installation of this project. And what I really like about this was sort of how lightweight it was, that we could sort of sequentially keep putting these modules together that would be constricting the global form into the dome, but the weight of the balls, you could still just go from the outside and lift it up slowly. So it was a really interesting construction process, because typically you'd go from sort of, if you're building a wall, you'd go from the bottom of the wall up. With the pneumatic, we kind of started from the top of the dome down. Sort of an interesting reversal. And this is sort of this was the realized first iteration of pneumatic masonry. You can see the hexagons and triangles in the image on the right here. Yeah, this wasn't for any client. It originally was supposed to go to Davos, Switzerland, but the client just fell out on us, and we had all the beach balls coming anyway, so we decided to make it in our own time in our friend's yard. But a few years later, we got approached to make a larger dome that would act as a bar for some music festival in Texas, and we were actually able to reuse the modules from the first pneumatic masonry by just inserting a row of beach balls between them. So here, the modules have no beach balls, no layer between them, but here you can sort of see the white kind of indicate the modules that we added to the system. And here's the result of that project. And as we're working through this, we're also thinking of ways to use the same idea to create different topologies, not just dome shapes, which are they're probably the strongest. But what we found was where the pentagons were happening, that's when you're creating positive Gaussian curvature. So you're doming a flat sheet. So if you had a flat sheet of hexagons and you put one node that had a neighboring 5 cells, it would begin to sort of curve the sheet downward. And inversely, if you had more balls around a specific node, like 7, which is you see in the blue, you get to have negative Gaussian curvature. So this was just something we were developing as we were playing around with different configurations of the system. And we haven't realized all of those different types of topologies yet, but this is sort of the evolution of the project that we call Pneumatic Masonry, where the top images, you sort of see the first iteration where it's just the triangular modules adding single sort of strut-like elements to it. We made a version with harnesses for each ball instead of molecules of balls. So we had sort of a harness system that you could create any module with a single ball. And that's the smaller white versions you see. And then finally on the bottom right, we recently acquired a machine that lets us weld our own airtight cells. And we were experimenting with not needing a harness at all. We actually just welded the hardware onto the inflatable itself, and we just used rope to lash the inflatables together. So it's sort of this ongoing evolution. I will be honest and say it's not the most practical solution, because you're having to inflate each individual cell separately, and it's only strong when everything's inflated. And when temperature differentials are a thing and each one is its own unit, it gets kind of messy, because all of the air will want to contract, and we can talk about that later in questions. So the next sort of high pressure system was this project that we completed pretty early on. We were starting out 2015, project called Pliescape, and we were asked to create a climbing structure for Burning Man. And this we kind of saw as this opportunity to see if we could make a multi-story inflated multi-story structure using inflatables as the main structural element. And it kind of started as this modeling process where we had a site model, and we were playing with this medical mesh and balls that would be supported between the nets, sort of like the project that I showed from Saraceno in Dusseldorf. And we quickly realized with the space we had that using spheres just took up too much volume in the footprint of the site that we were working with. So we switched to this type of pill-shaped geometry, just to save space, but also be able to separate the net layers with proper height. And once we kind of finished messing around with the physical models, I would then translate the positions of these inflated columns into Grasshopper and Rhino, and just come up with the relaxation of the netting, which this project, we did not make the netting. So this is one of the few projects I'm showing that we didn't make the elements involved. We worked with a cargo net company to produce the netting once we found the sort of layout that we wanted. And you can see what that kind of looked like in the red on the right there. And there are 2 layers of netting here, so they sent us both layers of the structure. And we also, so a big part of this is also before we had our welding capabilities. So we had to work with pre-bought objects, and these were actually ship fenders. They hang them off the side of big, large cruise ships to keep them from hitting the dock. So they're these really thick material that's welded, and they're rated for many, many pounds of force. And we ended up just buying 12 of these and just mocking up the structural components of what we're imagining in our backyard. We weren't really at a level where we're doing any engineering in the computer at this point. So you can see on the left, the first mock-up of just tensioning this column down with webbing straps and anchors. And then we ended up actually doing a half scale. Well, it's a full scale, but not the whole footprint of the structure we're going to do in the middle, where we had multiple layers to see if it could support 2 layers of the fenders, and then finally installing it on the ply at Burning Man. And it all packed up very small in the back of a truck. The net is the largest amount of weight of the structure, but we 4 people assembled this with no use of heavy machinery in like 2 or 3 days, which I think is pretty impressive for the site where we had, like, next to us there were teams of 14 people with big cranes and welding things. But I think that's another benefit of inflatables, is that you can really, with relatively minimal setup crew, you can make something pretty big. And here's a few shots of the climbing experience from the inside. It was really a fun project because it created these multiple layers of space that you can kind of climb through at any point. If you wanted to lounge in the middle layer, or just do some athletic climbing on the outside. Yeah, so that's that project. So Another shift from high pressure systems to projects that explore more transient qualities, I'd say. So light and color are sort of things that are unique to, well, I mean, sorry, fabrics and films in general are unique in the sense that you can let light through them. And that's a property that we have also explored in our work quite regularly. And this project was the first commission that we got, one of the first out of school in 2014 it was for a conference called Better World by Design. They just wanted a lounge space and had enough money for materials. So this is the project that kind of got us started as a studio. And the basic idea we had was to create a single membrane space out of transparent materials that were of the primary colors, and to see if we could get a complete color spectrum projected on the floor just from having the sun cross the rays of light after it passed through the material, to just sort of create this walking three-dimensional color wheel, basically. And it was a big learning process for us because we had to tackle a lot of the basic principles of single membrane spaces where you're actually entering into the pressurized space. So you need an airlock, you need a way to anchor this structure down, and you need a way to inflate it. So sort of the anatomy of the inflatable is just something that we were learning during this project. So we used tent stakes to anchor it down, and we developed this airlock that was actually, if you see on the left, a PVC hoop with a magnetic strip in the middle. So when you'd walk through the tension in the PVC hoop would want to create a flat plane on the door, and the magnetic strip would sort of self-lock it. So it was this sort of way to have the door close itself behind people. It's always a trade-off with these types of spaces because you want to allow for a lot of traffic, people going in and out, but you also don't want to let air out constantly. So that was sort of our solution for that. And on the right is sort of a shot from the inside. You can see the different colors projected on the floor, and we were able to get yellows between red and green, and turquoise between blue and green, and magenta between the blue and red. So that was a big exciting factor for us, and people really liked being in there. The floor was a soft material, and people would just go in and take naps and things like that. And just to show you a bit of our fabrication, this is the same process that we would have used for a single membrane like this at the time. We had an old 1970 pen plotter, architectural pen plotter, that we were loading brown paper in. And this is sort of what I was saying, where when you were making, every unique piece needed a template to be cut out. We tried using projectors before that, and it's not as nearly as accurate as sort of having a plotted full-scale template to work with. So we would basically load this brown paper in for all the unique pieces we needed to cut out, and then this brown paper would then be our template for all the pieces. And you don't need to watch us cutting out all of the pieces. The next step is, after the pieces are cut out, we use this process known as basting, where we pre-tape the edges of the inflatable with this double-sided sticky tape. That's what you see Levi doing with the yellow fabric back there on the left. And that allows us to stick the pieces together before we sew, so that when we sew through the tape, it kind of gunks up the hole created by the needle of the sewing machine, and it creates a much more airtight seam. It's not airtight, but it helps a lot when, you know, compounding the thousands and thousands of holes you do when you sew these things. It matters. So after we're done sewing the thing together, it rolls up to about the size of a human, weighs a little less. And I put the image on the right there just to show how these things are very soft until they reach pressure. So this was a particularly windy day, and you can sort of see the air being moved around until it has enough pressure to withstand the force of the wind. And this was very early on too, so we actually didn't use any coated fabrics. This was just, wasn't any plastic coating on the fabric itself. So air was escaping out of everywhere, but with a strong enough blower, just to show you that you can actually make inflatables out of many types of cloth, but it's better if you have coated fabrics, but that was another thing we learned. So that project sort of as our first single membrane space, I like to use this as a junction to describe the other main type of inflatable, which we call double membranes. And you can sort of imagine that if you're creating a space that you aren't going inside the pressurized space, but you have two layers of fabric that the air is inflated in the wall instead of in the primary space. That's what we call a double membrane. And we have done a bunch of double membrane structures in our practice, but the first one was this project we called the Fabric Prism on the right. And it stemmed from our explorations with color in the RG bubble, but we were wondering if we could modularize the color effect and sort of create cells on the outside of a double membrane that would induce this color combination of the primary colors onto an interior transparent surface, so we wouldn't have to deal with things like airlocks. But it was also just a novel, fun thing that we hadn't tried before. So the modeling for this is pretty simple. We just took the same sort of spherical geometry, wood tile, hexagonal tiling around it, and then we'd alternate pulling out vertices and pushing in vertices from the hexagonal tessellation to get this sort of cubic end shape. And the reason we were doing this shape is because in order to get the light to sort of commingle and project different combinations of the colors, we wanted to create as dimensional a cell as possible. So this was sort of our reasoning behind that. And then we would inflate the geometry in Kangaroo to sort of approximate how it would deform, but at the end of the day, we're still just cutting out the flat panels that you see in the bottom center. So Kangaroo for us is really good for form finding, see if wrinkles are happening, but at the end of the day, it's still a flat thing that we're unrolling. And so in terms of fabrication, this is typically what our process looks like. We'll have a sort of a 2D key that we're following, and because most of the time the inflatable itself just looks like a mess of fabric on the table when you start assembling it. It's one of those things that I think being in sort of like a world of like automating production and things like that is really interesting, because with sewing and soft goods, the material is so unpredictable that you can't ever really, I don't think there's going to be an automated seamster in the near future, because you have to, carry around this flexible piece of fabric and then align things, and you have a growing big piece of fabric that you're attaching smaller pieces to. And I think it's a process that is very hard to automate, let's just say. So a lot of our work kind of just becomes communicating production diagrams to us so that we don't get lost in this puzzle. So on the left, sometimes we feel fancy and we do a 3D print kind of key guide to how we assemble it. And in the middle, you sort of see the majority of our time is just spent sewing pieces onto the larger envelope. And with double membranes in particular, the last step, which is really fun, is going inside the inflatable and this one we physically tied rope of a set length to connect the outside of the double membrane to the inside, and that's what creates that cushion-like wall. So here's the project Inflating on another particular, I feel like I choose very windy days to take these videos. But so you can sort of just see how it differs from inflating the single membrane. These double membranes have a stance, and it's really nice because you can hide the ballast inside the wall of the inflatable. So it's a really clean way, and they're much more mobile, I'd say, than the single membranes, which you really need to lay out the whole foundation beforehand, and the previously mentioned problems with the airlocks and things like that. But on the right, you can see the colored spectrum displayed. on the interior fabric. The cool thing that's hard to show in this project is that over the course of the day, as the angle of the light changes to these cells, so does the color spectrum or the types of color you're getting on the inside. But it's also just a nice calm space to be in. And it's also nice that this coloring on the outside is it's kind of really changes based off of the angle you're approaching it. So on the outside, you see red and blue, but if you walk around a little bit, sometimes you can only see green. That's another fun aspect. So another type of sort of thing you can do with these membranes is not only let light in, but obscure light and sort of keep light out. So this next series of projects explored making small camera obscuras with pneumatics. And this project started as a commission from a couple of photographers at RISD, where Matt and I graduated from, who had been setting up this pinhole camera every year for this one event. And it was only up for 2 days, but it took them 2 days to install. It was like a big cardboard box. And for anybody that doesn't know, a camera obscura means dark room in Latin. It's just the most simple principle is if you take a light tight container and you poke a hole in it, you get an inverse image of the outside with no lenses on the opposite wall of the container. And so they approached us wanting a pop-up camera obscura, and we were very excited by the idea. So we ended up making them a single membrane spherical pinhole camera. And this is a shot from the inside. It had 4 apertures, 3 around the wall and 1 on the ceiling. So depending on where we placed it, you could see different vantage points, and you can see the ballast on the inside. We just had some sandbags arrayed around the border. Another project piece of this was we tried a different type of airlock with this structure. It's a same spherical geometry as, say, the room project, but we had this tent-like airlock where we had tent poles supporting the fabric in small anti. That you would load the people who are going in and then close the door and then open the main envelope to the space so the air would get caught before it got out. It's kind of scary thinking now that COVID is a thing, because it's a very small space with lots of people, but it was a new kind of airlock design for us. And yeah, so on the right, you can see a video of people moving in and out. The cool part about this is that the image is live, and if you're in a really busy part of the street, you get to see a lot of cars passing and people walking by. And so similarly to the fabric prism, after completing this project, we really wanted to sort of modularize this component and turn it into a double membrane space, not only because it was a really cool experience to be inside of this single image, but we realized we could use the opportunity to sort of create a compound effect where we could make different cells, like hundreds of them, and array them over the course of a dome, sort of like a fly eye or an insect eye. And so the main challenge here, because we're using lenses now, was figuring out the right lens to use with a proper focal length that would be the distance of the outside membrane to the interior surface. And we did a lot of physical tests, sort of getting the right distortion, because when we inflated it, the distance would change quite drastically. So this is a section view of the final design, where you can see it's the same thing, where we'd have, instead of a transparent layer on the outside, we have opaque fabric. Each one of these cells has a magnifying glass, and then on the interior surface is a translucent fabric. And instead of tying the 2 layers together, we had a piece of black fabric that we sewed between each layer so that light wouldn't spill from one cell into the next. So it's a bit different in construction than the fabric prism. And here's a video of an install of the compound camera. Again, these double membranes are really easy to install because you just have to set the footprint and plug in the blower. And some images from the inside of the projections. And it's a very strange experience because all of the images are inverted. So if somebody's walking around the structure, you see multiple of them upside down, walking the opposite direction than you think they're walking. So it's a very headache of a space, but it's also really beautiful. So we've set it up in a bunch of different places, but our favorite aspect of this is that you can focus the focal length. If you wanted to set your sights on something farther away than the structure, you can physically deform the membrane to change the focal length of the lens. And that was a really cool thing because it turned the entire structure and really used the pneumatic properties of this as a means of experiencing this optical effect. And I think it's very similar to how our eyes work, actually. It's just that we have muscles in our eyes that are distorting the envelope to focus on things of different distances. And I always like putting this in because this is sort of embarrassing to me, but the initial proposal is what you see on the left is sort of us imagining like huge lenses and big cones. And then what eventually the fabric, like the templating for these things are, quite toned down versions of this. And I end up having to go back in and re-simulate to create a better approximation of what this thing would become. Just to emphasize again that it's the physical form finding and physical making of the focal length and all that things is really what determines the aesthetic. And the simulation and things like that are really helpful, but it's funny that I have to go back in afterwards and make it look more realistic. So this last project that explores light and color actually was inspired from the first pinhole camera that we made. We sewed the whole thing together and we're picturing this really dark space. And when we went inside, we realized that all of the stitches that we had put inside the pinhole camera were leaving these tiny little pinholes all across the envelope, which was really beautiful, but we were also terrified because we needed a completely dark space. So we ended up having to tape them over. But we kept that in the back of our heads because it was this really nice effect. And we wanted to make a whole project just based off of letting light through in specific configurations. So we did a lot of these physical tests of welding black trash bags together, and we go inside with a little bit of smoke and we just take a pen and start playing with letting light in different areas or cutting slits in the envelope to let planes of light in. And we kind of settled on having this effect on a larger scale and using the seams as a means to let light through. So we were also experimenting with different modeling techniques. This is sort of how I showed in the Pneumatic Masonry project. We would print out these connectivity is dictating the topology of the sheet. So we have these nodes and just connect with these reeds. And we were playing around with different configurations of hexagons that could wrap into a three-dimensional object. And we kind of settled on this angled cone geometry because we knew that we needed a big surface area facing the sun. But also we wanted to make something a little bit different than a dome for once. So that was sort of our reasoning behind this exploration. And while we were doing the physical models, we also made sort of a digital simulation of, we would find the 2D layout of these nodes and struts, sort of to analyze how it affected the curvature of the sheet and what shape these placements of heptagons and pentagons create. So this is sort of a tetrahedral node that's being formed by just 9 heptagons, and the rest are just equal shaped hexagons, sorry. And so this was the model for the atmosphere piece that we ended up settling on. The sticky notes are just to show where the seams that we want to let light in through. And then the back end is sort of this tunnel that you enter through that also acts as the airlock, because this is also a single membrane continuous airspace. And the simulation really just helped us have a digital twin of this physical model that would help us in the end figure out the detail pieces like the border where it meets the ground and things like that, because the templating for this is quite simple. It's just 3 different pieces of fabric that we could just stack it and cut all at once. So heptagons, pentagons, and hexagons. And another thing we were trying out for this project, we got a new tool that's a hot air wedge welder. So inside the airlock, we had these airtight arches that were holding up the fabric. And this tool is a wedge of hot air that kind of swings in between the pieces of fabric that you're welding together. And it creates an airtight seal. And you need a coated fabrics with this. So it's melting the polymer that's on the fabric itself. And then these would be inflated and put into the airlock area of the tunnel that I was showing before. So this is us test inflating it in the studio. It's too big for our current space, but you can see the heptagons sort of at the branching area of the tunnel to the main cone space. And the arches I just showed are in that cylinder, the tunnel. And this is the finished piece facing south for the arts festival that commissioned it. And you can sort of see the blower box, and there's also a fog machine kind of nested there. It's not very pretty, but the black border that you see on the bottom is all the ballast we had to put out. But on the right, you see the interior projection of the light through the seam patterns. And again, this is nice to be in over the course of the day, because as the sun changes, so does these planes of light. And so the last sort of aspect I think is really cool about inflatables is adaptability, or sort of the ability for it to like exist in multiple states. So the last 2 projects I'll show address that in some way. This was a project we called the STEAM Pavilion. It was commissioned by the STEAM group at Brown, which just stands for Science, Technology, Engineering, Art, and Math. So they wanted a mobile lecture hall that could be used in different configurations. So the initial planning for this project was that it would be a hybrid structure. So we would have a reconfigurable single membrane space that you could tie the roof of, and a solid double membrane wall that was the airlock, but also support the single membrane space from the top. So on the right, you can sort of see different configurations that the group was interested in having for this lecture hall. And we ended up designing the membrane wall, which if you guys remember the problem of the airlock, it's something that usually isolates this problem to one part of the inflatable. And here, this is a solution we really liked, because it basically said, okay, let's make the entire wall of the structure an entrance point. And it kind of gets confusing because of, you don't know who's on the other side. But it was a really cool experience to watch people just enter at any point in the space just out of nowhere. So we kind of called it the diffusion of people through a semi-permeable membrane. And it held the air in fine, and we were able to get a pressurized interior space. But unfortunately, this project didn't really realize the tie down aspect of the design. We have all the sleeves sewn in the ceiling and all the webbing loops on the floor you can see on the right that are meant to be for tie downs. But another aspect of these, because they're very experimental, is that depending on where you are, different fire codes, like you need a really lightweight material to be able to pull it down and reconfigure it. So, but a structure of this size, you really need certain fire ratings and things like that. So unfortunately, we weren't able to realize the roof of this structure as designed, but it still acted as a conference space over the years. And I always like to show this because when we're installing this, it's typically one or two of us, and sometimes we're next to other people installing at temporary events. So it's like 10 people in a crane versus me who just plugged in a blower and walked away and started filming. So that's another really nice thing about inflatables, is that the pressure themselves does all the work of having to haul all this material around. So once you have it in place, it's relatively simple to erect. And the last project that I'll show is one of our more recent ones we call Canopy, and it stemmed from a lot of different experiments that we had done throughout the years of the ability sort of to inflatables to collapse and then redeploy. And the question then becomes sort of what shapes can accentuate this property, and how do you interact with the pressurization? So how do you turn it on and off the blower, or how do you trigger that event to happen? And on the left, you see that torus that's shrinking was actually part of Matt and I's thesis project before we started Newhouse, where we hooked up an EEG sensor, so like a brain node that is connected directly to a fan that would turn on and off based off of your level of focus. So there's a lot of playfulness that you can put with whatever input you want to trigger this inflation to happen. But this project, after doing some explorations formally, like the helix you see in the middle, or the geometry we eventually settled on the right, we were sort of interested in tiling these together and creating an effect where people could trigger one of these canopies to inflate next to another one. And we partnered with a friend of ours who ran a bike-powered smoothie company. He had a bunch of these stationary bikes that we could then hook up to batteries, which would be plugged into the blowers. And we kind of create this decentralized canopy effect, but you can see the bike there, which actually power the piece itself. And it's really cool because you can physically feel the resistance on the bike of how much power it would take to inflate something. Even this, it's relatively small for what we do, but it was a really great way to connect the energy consumption needed for one of these blowers to the human body, and create sort of a decentralized effect of this, people inflating and deflating it. So the last assembly graph I'll show, I promise, is just emphasizing how a lot of these things just come down to, figuring out your shape, unrolling it, and then labeling and figuring out a way to, lay these out when you're working on it so that you know what piece goes to what piece. With these types of lattice work or beams that go together, it gets kind of complicated because each scoop goes to a different piece. Like you see the piece shape on the right, every piece is relatively shaped like this kind of bat wing shape, but then each scoop corresponds to a different piece, and it's just this endless puzzle of figuring them out, which sort of brings me just to the end of the talk, or just sort of an outlook, where this is the current studio space we're in. We moved in about 5 or 6 years ago. It's much bigger so that we can install or test things inside of our studio now, rather than having to go outside or ask a friend to use their yard. And we've recently, or not so recently now, but when we moved in, we also got some new tools. So we have a CNC fabric cutter and the hot air wedge welder, which I outlined a bit before, and which let us cut a lot more complex objects without the need to print every template out of paper. And then the hot air wedge welder is really nice because we're able to create our own high pressure sealed inflatables. And thing to note with this is it's still a craft in itself. Like the use of this machine, we thought we'd get it and just be able to make airtight things like that, but it really requires a lot of effort and skill to use. So it's really important to us that we have this in the studio, and it's only through using these tools and realizing the limitations that we kind of design. So just to go back to the beginning of the talk, but now that we can cut all these things out, again, the problem becomes this sort of managing complexity. So an area of interest, and actually a project we're working on currently, is a lot of clients want sort of the minimum. They just want something that can keep the weather out and the sun out, but sort of just perform on a minimum level instead of these sort of more explorative light installations. Or and we've never really made a just a structure for that. So we call this project our utility dome, and the basic idea is that instead of having a single membrane or a double membrane, we'd have this air beam structure that would be filled with there'll be high pressure, and it would suspend a really thin inflated sleeve like a tent on the inside that would keep elements away. But the idea being with this is that you could have this structural element on the outside, or support the a thinner thing that could be replaced based off of whatever client wanted, a different color or something like that. So just trying to think of something a bit more utilitarian than our previous artworks. And then also in line with this project, trying to develop like automated assembly diagrams that help when we're laying this thing out and labeling it. So I've been looking a little into sort of graph theories on just like trying to key that kind of language into assembly diagrams or event-based sort of ways of doing a project, but that's still in development. And another area that we're really interested in is questioning the fabrics that we're making these things out of. So we've amassed a lot of knowledge about different types of materials over the years, but it's usually always ordering a roll of this thing and then cutting it out and reassembling it into this complex shape. So a project that we have a proposal out for now is exploring knits and pneumatics in two main different ways. One, we're imagining suspending knits inside of inflated envelopes. So the video that's playing on the left is a small model that Stavely, one of our members who's really amazing at knitting, made. And we're just suspending this inside of an envelope, which we imagine could be used as a space in itself, sort of a temporary complex shape that you could only get through knitting, or it could also be done as a formwork, maybe. And then the other aspect is using knits as sort of a constrictive sleeve for pneumatic envelopes, which you can build up. This is a Kevlar knit tube that we then just put a beach ball in, but you can get really high pressure. The knit will just restrict it, and it's really strong. It's like tear resistant. So that's actually a lot of what the space module is made of. It's like a Kevlar woven fabric that can resist micrometeors. Or anyway, so that's sort of it for me. I'm happy to answer any questions. Thanks for paying attention for that long. And yeah, thank you.
Thank you, August. That was really a kind of great kind of review of your work. I'm really impressed. I haven't seen it kind of live presented from one of you guys, so it's great to see. What I kind of like particular about it, that it really is a kind of a rich body of work, and you kind of really nicely explained how one idea of one project gets kind of picked up in another project. It's not necessarily sequential, but it's this kind of growing body of work, of interests and findings you have, that you kind of, once an opportunity comes, you kind of develop that further. It's really nice to see. It's something we don't see so often, so clearly in kind of architectural practice. It kind of, not in a formal way, but in a kind of methodological way, and this kind of continuous kind of design research project, it reminds me a bit of Mark Fournet's work, of the very many. But what is kind of then the question to me is, how do you operate as a collective? Yeah, I mean, you're three founders. You mentioned that you've got more experts on, and I can see in it, because knowing Mark, it's easy to kind of do that as a kind of single entity, a single author. But you kind of managed to do that as a collective, as a band. So how does that work? I'm seeing that it works, but I'm really curious to find out how does it work.
Well, I think it's something that it requires just well. First of all, it's something we're still figuring out because we've recently, not so recently, but in the past 4 or 5 years, taken on more people. And we originally founded under the name Newhouse as like a particular, it was for a project to get the correct insurance and things like that. So it wasn't something we were planning on in the beginning, but it's inherent because there were 3 of us when we founded. And I think in general, there's a lot of stuff that I didn't show that sort of keeps the, like, there's a business side of it too. Like, we've done a lot of commissioned work that isn't as explorative, and that's something to keep in mind. But in terms of the collective, I think we try to just open every project that potentially could bring, for example, this utility dome project that I shared at the very end was sort of a client really wants a specific thing, and if we see that a client could offer the opportunity to see something, to make something that we haven't done yet, we kind of flag that and bring it to the entire community. So we have a sit down with all of us at a table where we discuss sort of what this project could bring for Newhouse as a collective. And I think having that space to openly talk about incoming projects that might just be a really simple, like, we just have to make this, is important, but it's by no means, I would say, it's ever a finalized configuration of how do we keep the collective, I guess, what's the momentum going. It's just something that when we started, because there were multiple of us, we always had to be at the table in the very beginning of the process. And now that we're getting a bit bigger, I don't think we imagine us being more than, 10 people in the future, but I think I'm probably not answering your question, but I think that just having a space for new projects coming in that aren't just about being commercial, and having an open table where everybody at Newhouse can sit down and sort of start the conversation rather than starting it from one person's perspective. And that's another thing that I'll say is, if any one of us gave this presentation of our work, it would be completely different. So Matt and Levi and Stavely probably have their own perspectives on why these projects mean so much to them. So I'm sort of giving you the computational modeling side and fabrication side, because that's the things I'm involved with. But Matt, who's very material minded, or is really concerned with the details, so he'll probably get satisfaction from a project in a completely different way. So yeah, I hope that, I mean, if you have a specific question, I hope I didn't rant too long, but yeah, it is tough. And what I was saying before about sort of, we're an LLC now, and that's something that sort of maybe finding a business structure that makes the collective more apparent is another way you can go, but it's something we're still figuring out ourselves.
It's a perfect fine answer, and yeah, it's good to know, but it's also very quite an achievement, I would say, to have a company that has a business side and still manages to kind of pursue a certain design research interest of various members of your collective, so to say. I think that is, yeah, you don't see it that often, and it's something which is really great to see that you guys have that. I've got tons of questions. I've got 2 questions maybe from the audience. First is Victor, one of our researchers at the Institute. He's asking whether you are also interested in pushing the work some aspects of the work more towards kind of soft robots. You mentioned it at some instances, and is these walls of the steam pavilion kind of go into that direction, where, or they're kind of actuated things. What's your take on that?
Yeah, well, I think in the spirit of collective action, I think robotics is something that none of us are particularly like focused on, but like you said, the projects where, you know, we have these kinetic actuating inflatables are probably the closest to that. But we have had I think activating, like, our approach to it's a bit different when you start to scale these actuations, I'd say, because with a lot of soft robotics, it relies on this very controlled, or that I mean, there's different types, but it's usually like a silicone mold that creates different air cavities and different configurations, which is very controlled and sort of at a set scale. So I think at the scale you're working at, it's sort of it's similar to how I said, where those latex balloons, like translating those latex balloons to a larger scale, what we kind of had to switch material properties and fabrication techniques. And I'd say we're very interested in soft robotics, and I think there's a really cool area of sort of a macro soft robotic, like not getting too concerned with these airtight channels, but being able to actuate larger pneumatic envelopes, which I think could be really cool. But I guess the short answer to that is it's something that we have less of a focus on, but are totally willing to collaborate anybody who wants to work on a project on scaling soft robotics.
Fine. There's another question from Antonin, one of our students and student assistants here at the Institute. He thanks for the kind of inspiring lecture, and he wonders, as you mentioned in the very beginning, that these inflatables cannot only be filled with air, but with other gases. Whether you already kind of used or will use in the future light gases to float structures.
Yeah, so that was actually when we very first started out. I was really obsessed with creating an airship of some sort, like using helium or something like that. And it's kind of funny because as you learn more about, you know, fabricating these things and getting the right type of seam for holding in gases, you realize that everything leaks. Like everything leaks. Not even if you have a heat weld, there are particular materials that these sort of airship envelopes are being made out of that are fabricated on the highest level. So it's something that we're very interested in. And actually, the last well, it's not gas, but the last video is a friend of ours who is an aeronaut. He's a balloon pilot who shares studio space with us. We really want to do at least a hot air balloon, but in terms of gases, I think it's just a matter of budget and time, I think, with these types of things, because in order to create an envelope that can hold these like tiny little particles of helium or smaller, it just becomes a fabricatable feasibility kind of problem where it requires a lot of time and testing. And it's with the turnaround of our type of work, we haven't really had an opportunity to explore helium-filled structures yet. And I'm saying helium because there's other things you could fill it, but lighter than air is definitely something we would like to approach, but it'll probably start with something like a hot air balloon in the future before we get into gases. But yeah, that's just a short answer. It's mostly a material containment and fabricatability thing at this point.
Yeah, fair enough. Yeah, I mean, I think also kind of history has shown how at the beginning of the kind of the balloon, hot balloon, air balloon area, kind of showed how difficult it was to kind of just contain the helium in the balloon, and people were kind of making kind of very false assumptions on how long that would hold, and led to all sort of failed expeditions and so.
Yeah, conceptually, it's great. It's like if you can have an envelope that can just hold that gas all the time, then it's always there. But it's really hard to actually create that envelope.
Yeah. Another question from my side is what I really like about the Inflatables and how you kind of approach it, how you present it, is that it is most of the time it's a kind of a one-to-one kind of work. You sometimes do prototype, but the prototype is then sometimes only a section, or with the masonry just a couple of bubbles, and then you just kind of scale them in numbers, and there are then many people involved just to get the thing kind of going. I'm wondering to what extent you're taking kind of you outsource labor. Is it possible in the way you work at the moment, or is it just necessary that all of you just create that thing because it is not? It's kind of, your work is still kind of explorative or kind of a unique project. So it's kind of hard to kind of outsource stuff, or is that possible?
Yeah. So I wish Matt's probably in the YouTube chat somewhere, but he sort of does a lot of the material sourcing for us and research on sort of where we're getting our materials, but also fabrication techniques. And I think what he would say is that we're not opposed to outsourcing labor. I think the main point here is that we get a lot from fabricating everything in-house, like what you were saying about new ideas for projects comes from, sewing something together and thinking that it could be used in a different way. But we're not opposed to outsourcing labor. It's more a balance of, depending on what it is. Like if we have airtight things that we need made in a really particular way that we don't have the tools for, like a pool float or something like that, we'd outsource it. But we're always looking to actually acquire those tools for ourselves, because even if we outsourced it, it's much better to be able to explore with the process itself before sending it out to someone, so you can innovate on sort of how the thing is used. But we're by no means opposed to outsourcing. It's more just, if you send, we were actually thinking once, because we found, it was actually flattering, I'd say, but we found one of our pictures from our website on Alibaba, and they basically were selling the fabric prism for $2,000 or something. And we were just curious of what if we just ordered it, and just seeing like how well it would be made, or how they would actually execute it. Because there's a lot of places that fabricate things. Like in China, there's a lot of inflatable production happening, and at a really high end. And it would be something, I think, in short to the question is, like, if we were to outsource something, we'd approach the project starting with the idea that we're outsourcing this, and working with sort of that as one of the main ideas. So we probably wouldn't make it this crazy complex thing, but yeah. That's a blurred answer, but in general, we're not opposed to it. It's just we like having it in-house because we learn a lot from working with the material at the correct scale. And if we outsourced everything, we probably wouldn't be as inspired.
Yeah, Matthew seems to be on the YouTube chat, and he approves your answer. That's the correct answer. Just one follow-up on that topic is kind of, I know you guys also do kind of workshops on inflatables. Probably do that with kind of design students and so. But on the other hand, how accessible is that to kind of non-trained general public type of people who are interested doing that sort of stuff? Is kind of communal work, or I know, Thomas Saraceno, at some point, he kind of takes it to his extreme, welding plastic bags together to kind of huge air balloons with the community. Have you done something like that, where you work with just high school kids?
Yeah, we've done a lot of workshops where it actually, for larger envelopes, it lends itself to community building, because if you say you have a big envelope patterned and you need like hundreds of things cut out and put together, it kind of, the arc of building an inflatable actually follows the arc of sort of communities kind of coming together, but there's at the very end, there's usually a bottleneck because you can usually have a lot of people working on something, taping together different sections, but there's always a moment where kind of one thing has to become whole. But we've done a bunch of projects where it's very similar to the Saraceno stuff, but not with plastic bags, but with different scraps from our studio. And it's really cool. And I think it's something we'd like to continue in the future, just thinking of decentralized approaches too. Like you could send out one piece that needed to be cut out or something, and everybody just brings that one piece to like a meeting spot where you assemble an envelope. But yeah, we've done a lot of workshops like that. And I think in general, to your DIY kind of, if anyone can approach it, there are a lot of, like, similar to the taping and welding with a clothing iron, there's a lot of ways to just get immediately into this type of work that it's very accessible. And I think inflatables as a medium in general, that's how we started out, is because most of the things, it's a way to iterate really quickly at a big scale with materials that are really cheap and accessible. And at the end of the day, it's just the minimum viable way to create space. It's like a thin sheet of plastic that you can just weld together. For welding, I'd recommend there's a DIY pack raft YouTube channel where they do a lot of really in-depth tutorials on how to weld airtight boats, but it's all done with just by hand. So I can send that to you if you're interested.
Yeah, I mean, I would have tons of technical questions, but I'm not going there today. There's one last question probably from Jan Philip, one of our researchers here. And he asks whether you are interested in kind of outer space inflatables, kind of inhabiting other planets, working with different atmospheric pressures. There are no atmospheric pressure at all to make inhabitable artificial environments.
Yeah, I mean, that's one of our biggest dreams, is to be able to create something that goes into outer space. And I think getting there, I could see it happening in a variety of ways. Like if we reach a level of fabrication technical ability, then maybe they'll approach us to fabricate some of these things, or maybe the commercial space industry will be far enough along that they'll commission us to design some zero gravity playground. That's my dream, but I'm sure there'd be other ways to approach that. But yeah, just one more comment on that is that one of our least favorite things to do during every project is cutting something at a ground plane, because with a lot of these pneumatic forms is that everything wants to round out. So I think having an orientless, or what's the word for it? No orientation in just floating in space. We've always imagined a lot of these forms to be really, not only it would be beautiful to experience, but maybe some space station design could leverage just sort of like three-dimensional networks that are suspended inside of some envelope. But and it's short answer is yes, we'd love to, but it's more maybe in time.
but I haven't seen, I mean, having seen many kind of architects, designers venturing into the kind of race to Mars recently. I mean, there are some kind of pretty kind of wild proposals being made, which have been taken quite seriously from the kind of community. So yeah, I think
for sure.
The opportunity is probably more than ever out there to kind of follow that.
Yeah, all right, we got to change gears. We're going into space.
Yeah. Yeah. Oh, thank you very much. Thank you and your colleagues, Matthew, from joining the chat. Yeah, I would be very keen to kind of meet for a workshop or so in some point in the future. Trying to make
we'd love to. Yeah, that'd be great.
Let's find a format for that, and I will follow your work and kind of curious for the next projects to come. Thank you.
Thanks.
Good. Thanks everyone out there. See you soon. Bye bye.
Bye.